A single-displacement reaction, also named single-replacement reaction, is a type of oxidation-reduction chemical reaction when an element or ion moves out of one compound and into another, that is, one element is replaced by another in a compound. This is represented by the general reaction scheme. This will most often occur if A is more reactive than B. A and B must be either different metals, in which case C represents an anion, or halogens, in which case C represents a cation. In either case, when AC and BC are aqueous compounds, C is a spectator ion. In the activity or reactivity series, the metals with the highest propensity to donate their electrons to react are listed first, and the most unreactive metals are listed last. Therefore, a metal higher on the list is able to displace anything on the list below it. The order of activity for metals, from most reactive to least reactive, is Li, K, Sr, Na, Ca, Mg, Al, Zn, Cr, Fe, Cd, Company, Ni, Sn, Pb, H, Sb, As, B, Cu, Hg, Ag, Pd, Pt, or. Similarly, the halogens with the highest propensity to acquire electrons are the most reactive. The activity series for halogens, from highest to lowest, is F, Cl, Br, I. Due to the free state nature of A and B, all single-displacement reactions are also oxidation-reduction reactions, where the key event is the movement of electrons from one reactant to another. When A and B are metals, A is always oxidized and B is always reduced. Since halogens prefer to gain electrons, A is reduced and B is oxidized when A and B represent those elements. A and B may have different charge as ions and therefore some balancing of the equation may be necessary. For example, a reaction between silver nitrate, AgNO3, and zinc, Zn, forms silver, Ag, and zinc nitrate, Zn, NO3, 2. 2-AgNO3, Ag, plus Zn, S, A2-Ag, S, plus Zn, NO3, 2, Ag. All simple metal with acid reactions are single-displacement reactions. For example, a reaction between magnesium, Mg, and hydrochloric acid, HCl, forms magnesium chloride, MgCl2, and hydrogen, H2. Mg, S, plus 2HCl, Ac, AmGCl2, Ac, plus H2, G. Cation replacement, one cation replaces another. A cation is a positively charged ion or a metal. When it is written in generic symbols, it is written out like this: X plus YZ or XZ plus Y, element X has replaced Y in compound YZ to become a new compound XZ and the free element Y. This is an oxidation-reduction reaction wherein element Y is reduced from a cation into the elemental form and element X is oxidized from the elemental form into a cation. Some examples are Cu plus 2-AgNO3 or 2-Ag plus Cu, NO3, 2, Fe plus Cu, NO3, 2 or Fe, NO3, 2 plus Cu, Ca plus 2 hours 2O or Ca, OH, 2 plus H2, Zn plus 2HCl as ZnCl2 plus H2. Note that if the reactant in elemental form is not the more reactive metal, then no reaction will occur. Some examples of this would be the reverse reactions to these: Ag plus Cu, NO3, 2 a no reaction, or plus HCl a no reaction. Anion replacement, one anion replaces another. An anion is a negatively charged ion or a known metal. Written using generic symbol, it is A plus XY or XA plus Y, element A has replaced Y to form a new compound XA and the free element Y. This is an oxidation-reduction reaction wherein element A is reduced from the elemental form into an anion and element Y is oxidized from an anion into the elemental form. Some of the few examples that involve halogens are shown here: Cl2 plus 2 and ABr2 and ACl plus Br2, Br2 plus 2Ki or 2Kbr plus I2. Again, the less reactive halogen cannot replace the more reactive halogen, I2 plus 2Kbr a no reaction. Reduction of metal halides based on single-displacement reaction. This section discusses a number of industrial applications for single-displacement reaction. Metallothermic reduction of metal halides is quite well established and in some cases used on large industrial scale for production of metals and metal alloys and compounds. Below is an extensive compilation of reduction reactions for metal chlorides with sodium, calcium, magnesium and aluminium. A significant number of the reactions discussed below are used on large scale for production of all kinds of materials, including pure metals, alloys and compounds, with many examples in the patent and scientific literature. 1. Sodium, 3Na plus Al Cl3 3NaCl plus Al, S, 3Na plus Br Cl3 3NaCl plus Br, S, 2Na plus CoCl2 2NaCl plus Company, S, 3Na plus CrCl3 3NaCl plus 2Cr, S, 2Na plus NiCl2 2NaCl plus Ni, S, 2Na plus PbCl2 2NaCl plus Pb, S, 3Na plus FeCl3 3NaCl plus Fe, S, 2Na plus CuCl2 2NaCl plus Cu, S, 3Na plus ScCl3 3NaCl plus 3. Sc, S, 4Na plus TCl4 4NaCl plus T, S, 3Na plus TCl3 3NaCl plus T, S, 4Na plus VCl4 4NaCl plus V, S, 4Na plus WCl4 4NaCl plus W, S, 4Na plus ZrCl4 4NaCl plus Zr, S. Sodium reduction of metal chlorides is favorable and has been used on an industrial scale for production of metals and alloys. Usually powders of the chlorides are reacted with molten sodium chlorides and the byproduct is sodium chloride. The disadvantage with this approach is that the reduction is highly exothermic and the byproduct is very stable. Further processing is required to get rid of NaCl. For production of alloys, a mixture of the chlorides are reacted with Na to produce the required composition, for example 7Na plus FeCl3 plus NiCl2 plus CoCl2 or FeNiCo plus 7NaCl, 2. Calcium, Ca plus CoCl2 or CaCl2 plus Co, S, 3Ca plus 2CrCl3 or 3CaCl2 plus 2Cr, S, Ca plus CuCl2 or CaCl2 plus Cu, S, 3Ca plus 2Al-Cl3 or 3CaCl2 plus 2Al, S, 3Ca plus 2FeCl3 or 3CaCl2 plus 2Fe, S, Ca plus NiCl2 or CaCl2 plus Ni, S, Ca plus PbCl2 or CaCl2 plus Pb, S, 2Ca plus 3ScCl3 or 2CaCl2 plus 3Sc, S, 2Ca plus TCl4 or 2CaCl2 plus T, S, 2Ca plus VCl4 or 2CaCl2 plus V, S, 2Ca plus ZrCl4 or 2CaCl2 plus Zr, S, 2Ca plus WCl4 or 2CaCl2 plus W, S. Calcium reduction of metal chlorides is favorable for production of metals and alloys. Usually, the chlorides, in a powder form or in a vapor form, are reacted with molten calcium and the byproduct is calcium chlorides. The disadvantage with this approach is that the reduction is highly exothermic and the byproduct is very stable. Further processing is required to get rid of CaCl2. For production of alloys, mixtures of the chlorides are reacted with Ca to produce the required composition, for example 5Ca plus 2FeCl3 plus NiCl2 plus CoCl2 or Fe2NiCo plus 5CaCl2, 3. Magnesium, Mg plus NiCl2 or MgCl2 plus Ni, S, 3 mg plus 2BrCl3 or 3MgCl2 plus 2Br, S, Mg plus CoCl2 or MgCl2 plus Co, S, 3 mg plus 2CrCl3 or 3MgCl2 plus 2Cr, S, Mg plus CuCl2 or MgCl2 plus Cu, S, 3 mg plus 2FeCl3 or 3MgCl2 plus 2Fe, S, Mg plus PbCl2 or MgCl2 plus Pb, S, 3 mg plus 2Al-Cl3 or 3MgCl2 plus 2Al, S, 2 mg plus 3ScCl3 or 2MgCl2 plus 3Sc, S, 2 mg plus TCl4 or 2MgCl2 plus T, S, 5 mg plus 2 tar Cl5 or 5 mg Cl2 plus 2 tar, S, 2 mg plus 4 VCl4 or 2 mg Cl2 plus V, S, 2 mg plus WCl4 or 2 mg Cl2 plus W, S, 2 mg plus ZrCl4 or 2 mg Cl2 plus Zr, S. Magnesium reduction of metal chlorides is favorable and has been used on an industrial scale for production of metals and alloys. Mg is quite popular for reduction of chlorides and is used on a large scale for production of titanium, zirconium and many other metals and alloys. Usually, the metal chlorides, in a powder form or in a vapor form, are reacted with Mg powder or with molten vapor Mg, and the byproduct is magnesium chlorides. The main advantages of using magnesium are that Mg is cheap, easy to handle and is widely available. The disadvantage with this approach is that the reduction is highly exothermic and the byproduct is very stable. Further processing is required to get rid of MgCl2. Also, there is the possibility of formation of magnesium compounds. For production of alloys, mixtures of the chlorides are reacted with Mg to produce the required composition, for example 5 mg plus 2 FeCl3 plus NiCl2 plus CoCl2 or Fe2NiCo plus 5 MgCl2, 4. Aluminium, 2Al plus 3 CoCl2 or 2AlCl3 plus 3 Co, S, Al plus 3 CrCl3 AlCl3 plus Cr, S, 2Al plus 3 CuCl2 or 2AlCl3 plus 3 Cu, S, 2Al plus 3 CaCl2 or 2AlCl3 plus 3 Ca, S, Al plus FeCl3 AlCl3 plus Fe, S, 2Al plus 3 NiCl2 or 2AlCl3 plus 3 Ni, S, 2Al plus 3 PbCl2 or 2AlCl3 plus 3 Pb, S, 4Al plus 3 TCl4 or 4. AlCl3 plus 3T, S, Al plus TCl3, S, AlCl3 plus T, S, 4Al plus 3 VCl4 or 4AlCl3 plus 3V, S, 4Al plus 3 ZrCl4 or 4AlCl3 plus 3 Zr, S, 4Al plus 3 ZrCl4 or 4AlCl3 plus 3 Zr, S. Aluminium reduction of metal chlorides is favorable and has been used for production of metals and alloys. Usually, the metal chlorides, in a powder form or in a vapor form, are reacted with Al powder or with molten Al, and the byproduct are aluminium chlorides. The main advantage of using aluminium is that aluminium chloride sublimes at low temperature and then the required metals or alloys are produced in a pure form with no need for further processing. The use of Al powder as a reducing agent is attractive as it allows mixing with the metal chlorides powder in a solid form at low temperatures. Al is also widely available and cheap. One form of this reduction is the standard Alumina thermic reduction process using metal chlorides instead of oxides. The disadvantage with the Al reduction route is that the reduction is exothermic and formation of aluminides is favorable with an accompanying loss of reaction efficiency. For production of alloys, mixtures of the chlorides are reacted with Al to produce the required composition, for example 7Al plus 3 FeCl3 plus 3 NiCl2 plus 3 CoCl2 or 3 FeNiCo plus 7AlCl3. See also, double displacement reaction, substitution reaction, synthesis. References: Bach, Hans Dieter. Hazari, Al. Yitbrook, Silchi. Misconceptions in Chemistry Addressing Perceptions in Chemical Education. Berlin, Springer pages 227-228. ISBN 3540709894. Brown, LeMay, Burston. Chemistry: The Central Science, 10th ed. Pages 143. Pearson Prentice Hall 2006, Silberberg. Chemistry: The Molecular Nature of Matter and Change, 4th ed. Pages 150. McGraw-Hill 2006.